Imagine 50 million people watching a baseball game on television when the broadcast suddenly cuts to static and the stadium begins to shake. For a few seconds, before any official word had reached anyone, that image of empty air and trembling cameras told a story that the scientific community would spend years working to fully understand. Tonight, I am here with Rowan Hartsteele.
Good evening, Clara.
There's an earthquake that struck one of the most seismically studied regions on Earth, and still managed to surprise the scientists who had spent careers preparing for it, an event that revealed how much remained unknown about the ground beneath one of the world's major cities. Tonight, we turn to a seismic event that became a turning point, not only in disaster response, but in the scientific understanding of how faults behave and why that behavior can still confound even the best prepared researchers. The question before us is how a 15-second event in the hills south of San Francisco forced scientists to reconsider fundamental assumptions about one of the most studied fault systems in the world.
The answer begins not with the earthquake itself, but with the scientific confidence that preceded it, and with what that confidence got wrong.
We are speaking about the Loma Prieta earthquake.
The Loma Prieta earthquake struck Northern California on the evening of October 17, 1989, with a magnitude of 6.9, rupturing a section of the San Andreas Fault beneath the Santa Cruz Mountains and producing one of the most consequential seismic events in modern American history.
Then let us begin with the fault itself, and with what scientists believe they understood before that evening.
The San Andreas Fault is the boundary between the Pacific Plate and the North American Plate, two of the major tectonic plates whose movement shapes the geology of western North America. The fault runs approximately 1,300 kilometers through California, from the Salton Sea in the south to Cape Mendocino in the north, passing directly through or near some of the state's most densely populated regions grandes. By 1989, the San Andreas was among the most intensively studied geological features on Earth. A decade of research following the devastating San Francisco earthquake of 1906 had produced detailed maps of the fault's surface trace, measurements of the rate at which the two plates moved relative to each other, and increasingly sophisticated models of how seismic energy accumulated and released along its length.
So the scientific community had decades of data and well-developed theoretical frameworks to work with.
Yes, and this is precisely where the story becomes scientifically interesting. The existence of detailed models did not mean that all aspects of fault behavior were well understood. It meant that certain assumptions had become deeply embedded in how researchers thought about seismic risk. One influential framework at the time was the concept of seismic gaps, the idea that segments of a fault that had not produced major earthquakes in a long time were accumulating stress, and were therefore more likely to rupture in the near future. Under this framework, the section of the San Andreas Fault beneath the Santa Cruz Mountains, which had not produced a major earthquake since 1906, was indeed identified as a candidate for future rupture. In that narrow sense, the location of the earthquake was not entirely surprising.
Though the location was within the range that models had considered, but the behavior of the earthquake was not.
Exactly. And this is the crucial distinction that separates Loma Prieta from a simple confirmation of existing theory. The earthquake occurred at a depth of approximately 18 kilometers, significantly deeper than the portion of the fault that most models had focused on. It also involved a combination of strike, slip, and thrust motion, meaning the two sides of the fault did not simply slide horizontally past one another, but also moved vertically. This complexity in the rupture mechanism had not been clearly anticipated, and it had significant implications for how seismic energy was distributed across the landscape, and why certain areas were more severely shaken than simple distance from the epicenter would have predicted.
So the surprise was not simply that an earthquake happened. It was that the earthquake revealed structural complexity the existing models had not captured.
Yes, and we will return to those scientific implications. But first, let us understand what happened on the ground in the moments the earthquake struck. The earthquake struck at 5:04 in the afternoon local time on October 17, 1989. The timing was consequential in two directions at once. On one hand, the World Series was being played that evening at Candlestick Park in San Francisco, between the San Francisco Giants and the Oakland Athletics. Tens of thousands of people were inside the stadium, and an estimated 60 million viewers were watching the pre-game broadcast on national television when shaking began. The live television cameras captured the moment of the earthquake as it happened, producing footage that was broadcast immediately across the country and around the world. For most Americans, This was their first experience of watching a major earthquake unfold in real time.
So the earthquake entered public consciousness at the moment of its occurrence, with unprecedented immediacy.
Yes. But the timing also had a less noted effect. Because it struck in late afternoon, many commuters were still in their vehicles on highways and bridges rather than at home or at work. The implications of this for casualties were severe. The single greatest loss of life in the earthquake occurred at the Cypress Street Viaduct, an elevated double-deck freeway in Oakland. A section approximately 1.5 kilometers long collapsed, with the upper deck falling onto the lower deck, trapping or ending the lives of motorists who had no warning and no possibility of escape. 42 of the 63 people who lost their lives in the earthquake were in that collapse. The structure had been built in the 1950s to engineering standards that subsequent seismic research had already identified as insufficient. But the cost and logistical difficulty of replacing it had deferred action.
So again, as in many disasters, the infrastructure failure had been identified before the event.
Yes, the Cypress Viaduct had been assessed and flagged for seismic vulnerability, but the retrofit had not yet been completed. The earthquake arrived before the calendar of planned improvements could reach it. The Bay Bridge, which connects San Francisco and Oakland and carries approximately 270,000 vehicles per day, also sustained damage. A section of the upper deck on the eastern span fell onto the lower deck, closing the bridge entirely for a month and disrupting transportation across the region for far longer. In San Francisco, the Marina District suffered severe damage disproportionate to its distance from the epicenter. Buildings sank, tilted, and collapsed. Fires broke out that were difficult to control, because the earthquake had also damaged water mains.
So the Marina District was more severely affected than its distance from the fault would have suggested.
Yes, and that question became one of the most scientifically significant outcomes of the disaster. The Marina District is built on land that was created partly from debris deposited during the reconstruction after the 1906 earthquake, including rubble and loose fill placed in what had been a shallow bay. This material behaved very differently from solid bedrock when subjected to seismic shaking. The phenomenon is called liquefaction, when loose, water-saturated soil is subjected to the rapid back-and-forth motion of an earthquake. The soil particles lose contact with one another, and the ground temporarily behaves like a liquid, rather than a solid. Structures built on such ground sink, tilt, or collapse.
So the ground itself failed, not just the buildings on top of it.
Yes, and liquefaction had been documented and studied before Loma Prieta, but the vivid and extensively photographed example provided by the Marina District gave the concept unprecedented public and scientific attention. It also demonstrated that the seismic risk maps being used for land use planning and building codes at the time did not adequately account for the amplification of ground motion in areas with specific soil conditions. In Santa Cruz, the town closest to the epicenter, the historic downtown area experienced severe structural damage. A section of the Pacific Garden Mall, a pedestrian shopping area, lined with older unreinforced masonry buildings, collapsed, and several people lost their lives there.
So, the pattern of damage told multiple different stories about vulnerability depending on soil type, construction age, and structural design.
Exactly, and reading that pattern was one of the most productive scientific activities that followed the earthquake. Each building that collapsed or survived told researchers something about which design assumptions had held, and which had not. Now, let us turn to the scientific response, because this is where Loma Prieta's historical significance extends beyond disaster management into the advancement of fundamental knowledge. By 1989, California had a more extensive network of seismic instruments than any comparable region in the world. Hundreds of seismometers and strong motion accelerometers had been deployed across the state, many of them installed specifically to study the San Andreas fault system. When the Loma Prieta earthquake struck, all of those instruments recorded it simultaneously. The result was a dataset of extraordinary richness, the most detailed record of a major California earthquake that had ever been collected.
So the earthquake arrived into a scientific environment that was precisely prepared to document it.
Yes, and what that documentation revealed challenged existing models in important ways. Analysis of the seismic records showed that the rupture did not propagate along the surface trace of the San Andreas fault, where it was visible on maps. It occurred on a section of the fault that was blind at depth, meaning it did not break through to the surface at all. This was a significant finding. It meant that surface mapping of faults, which had been a primary tool for identifying seismic hazard, could miss hazardous fault sections entirely. because some segments of a fault system are not visible at the surface, even when they are capable of generating major earthquakes.
Though the tools that scientists had used to identify dangerous faults were incomplete in a way they had not fully recognized.
Yes, and that finding cascaded into a re-examination of seismic hazard assessments, not only in California but in other tectonically active regions around the world. The data also revealed that the earthquake involved a combination of fault motion types, the oblique slip already mentioned, that produced an asymmetric distribution of ground shaking. Some areas received more intense shaking than their distance from the rupture zone would have predicted, while others received less. This directivity effect, in which the energy released by the rupture is focused in certain directions depending on how the fault breaks, was understood theoretically before Loma Prieta, but had not been so clearly documented with real earthquake data at this scale.
So the earthquake provided real-world confirmation for theoretical concepts that had not previously been validated at this level of detail.
Yes, and this pattern of the earthquake advancing theory by providing data that tested and refined existing models ran through virtually every dimension of the scientific response. The concept of fault segmentation, the idea that a major fault like the San Andreas is not a single uniform structure, but a collection of distinct segments with different geometries, depths and mechanical properties, was significantly advanced by Loma Prieta research. Understanding how segments interact, whether a rupture on one segment can trigger rupture on adjacent segments, and what controls the extent of a given earthquake, became central questions in the research programs that followed.
So Loma Prieta did not answer the major questions about the San Andreas. It sharpened them.
Exactly. And that sharpening is one of the most important functions a major scientific event can perform. It is more productive to know precisely what you do not know than to operate under the illusion that you do. The earthquake also provided the most extensive dataset yet for studying aftershock sequences, the smaller earthquakes that follow a major rupture as the surrounding rock adjusts to the stress changes produced by the main event. Thousands of aftershocks were recorded over the weeks and months following the main event, allowing seismologists to map the three-dimensional structure of the fault zone with a precision that ground mapping alone could never have achieved.
So the fault revealed its own geometry through the pattern of its continuing activity.
Yes, the fault in a sense imaged itself, and those images informed the next generation of seismic hazard maps used for building codes and land use planning across California.
Before we close tonight, let us take a brief pause and welcome Margaret Evernight. Margaret, for those who want to understand the science of the Loma Prieta earthquake in greater depth, where would you invite them to continue in?
Thank you, Clara. In this case, the most direct path is also the most important one. I would suggest beginning with the United States Geological Survey's comprehensive study, the Loma Prieta earthquake of October 17, 1989.
So, this is a primary scientific document, rather than a popular account.
Yes, it examines the geological setting, rupture dynamics, ground motion patterns, and structural damage of the earthquake in detail. It also documents how the event contributed to advances in seismic monitoring and changes in building standards designed to reduce the impact of future earthquakes. For a reader who wants to understand what the earthquake actually told scientists and how those findings were translated into practical improvement, this is the most authoritative source available.
Is it accessible to a reader without a background in geology or seismology?
It is a technical document and will challenge readers without scientific background in places. But its structure allows a reader to engage with the sections most relevant to their interest, and many of its findings are summarized in language that rewards careful reading even without specialist training. It is the kind of document that shows how science actually works after a major event, how data is gathered, interpreted, debated, and translated into knowledge that changes practice.
So reading, it gives a reader not only the findings but the method behind them.
Yes, and that combination is rare and genuinely valuable for anyone who wants to understand how scientific understanding of natural hazards is built.
Thank you, Margaret. That is a thoughtful place to pause tonight.
Thank you, Clara. It was a pleasure.
The legacy of the Loma Prieta earthquake operates across several distinct but interconnected domains, each of which has had lasting consequences. In engineering and infrastructure, the earthquake triggered the most extensive seismic retrofit program in California's history. The Cypress Viaduct was demolished rather than repaired, and a new ground-level boulevard was built in its place. The Bay Bridge's eastern span was eventually replaced entirely after years of debate about whether it could be adequately strengthened. A replacement completed in 2013. Thousands of older buildings across California were assessed and retrofitted under new standards that Loma Prieta had made politically impossible to defer further.
So the earthquake accelerated a program of infrastructure improvement that had been building in policy discussions for years but required a visible catastrophe to move decisively forward.
Yes, and this dynamic, where known vulnerabilities are addressed only after they produce visible harm, rather than before, is one of the most consistent and troubling patterns in the history of disaster policy. In seismic science, the advances that followed Loma Prieta were substantial. New methods for analyzing the three-dimensional structure of fault zones were developed and applied, not only in California but globally. The earthquake led directly to increased investment in seismic monitoring networks. The Advanced National Seismic System, a coordinated national network of seismic instruments, was significantly expanded in the years following the disaster, increasing the density and quality of data available for future earthquake analysis. Probabilistic seismic hazard analysis, a framework for expressing the likelihood that shaking of a given intensity will occur at a specific location within a defined time period, was refined and became the standard tool for communicating seismic risk to engineers, planners, and policymakers.
So the earthquake contributed to a shift from describing what a fault might do to estimating the probability that it would do it within a given time frame.
Yes, and that probabilistic language, while technically demanding, allowed seismic risk to be communicated in ways that could be directly incorporated into building codes, insurance models, and land use regulations. The discovery of blind thrust faults as a significant hazard class also altered how hazard assessments were conducted in urban areas worldwide. The recognition that dangerous faults do not always leave surface traces prompted the development of new geophysical methods to identify and characterize subsurface fault structures. These methods have since been applied in the Los Angeles Basin, in the Seattle area, in Japan, in Turkey, and in many other regions where blind faults have been identified as significant contributors to urban seismic risk.
So the lessons of Loma Prieta spread beyond California into the broader global practice of earthquake science and urban planning.
Yes, and in the domain of public understanding, the earthquake had a lasting effect on how Americans thought about seismic risk. Because of its timing during a nationally televised broadcast, Loma Prieta was experienced vicariously by tens of millions of people who were not in California. The images of collapsed highways, burning neighborhoods, and the shaking stadium created a visceral public understanding of earthquake consequences that no educational campaign could have replicated. In the years following the earthquake, public interest in earthquake preparedness increased measurably. Emergency supply stockpiling, household retrofit programs, and workplace preparedness training all saw increased participation across the Bay Area and beyond.
So the visibility of the disaster served a function that scientific communication about earthquake risk had not been able to achieve alone.
Yes, and this raises a question that remains unresolved in disaster science and public policy. The awareness generated by a catastrophic event is real and valuable, but it is also temporary. Within a few years, preparedness behaviors that had increased after Loma Prieta began to decline as memory of the event faded. How to maintain sustained public attention to low probability but high consequence hazards, particularly when those hazards may not materialize for decades or longer, is one of the enduring challenges of risk communication that Loma Prieta highlighted without resolving.
So the earthquake taught scientists and policymakers not only about faults but about human attention.
Yes, and today, as California continues to plan for the major earthquakes that scientists regard as inevitable along the southern San Andreas and other active faults, the scientific framework built in the years following Loma Prieta shapes every aspect of that preparation. The building codes, the hazard maps, the monitoring networks, and the probabilistic models used to evaluate seismic risk all carry the imprint of what was learned from 15 seconds of ground motion in the Santa Cruz Mountains in the autumn of 1989.
So, the earthquake is still speaking to the scientists and engineers working on the next one.
Yes, the ground beneath California has not finished moving, but the science used to understand it is more capable than it was before the Earth moved that October evening.
Thank you for staying with us tonight. And thank you, Rowan, for guiding us through the geology, the destruction, and the lasting scientific legacy of the Loma Prieta earthquake.
15 seconds of motion reshaped decades of assumption. That is the compressed lesson of every earthquake that surprises those who thought they understood the fault.
If this conversation stayed with you, you are welcome to like, comment, and subscribe. You'll find other episodes here where history, ideas, and power are approached slowly. Until next time, stay with us.